Welcome to the 16th lecture in the open course on diffusion in multi-component solids. In this lecture, we will derive continuity equation which along with Fick's law establishes dependence of concentration on time and distance coordinate. We will also solve diffusion equation for steady state diffusion condition in this lecture. So now we have gone through Fick's law and also the application of Fick's law in multi-component systems. We saw that we need at least n minus 1 square interdiffusion coefficients to describe diffusion in n component system, right, which means if we have a ternary system we need 4 interdiffusion coefficients, for quaternary we need 9 and so on, and they are again all functions of composition. So, let us come back to binary system. In binary system we showed that we need only one interdiffusion coefficients. So, the diffusion flux of both the components is described based on only one interdiffusion coefficients, and this interdiffusion coefficient again varies with composition. So, if we write Fick's law for binary system, we write J I tilde, tilde sign here again I mention denotes that we are talking about interdiffusion or intermixing or diffusion along the strong concentration gradients. J I tilde, that is the interdiffusion flux of I, is equal to minus d tilde times the gradient of concentration of I with respect to the distance coordinate dou C I by dou x. Now, we know that the concentration varies as a function of distance coordinate as well as time, right. So, if we consider a particular diffusion zone and at some time t1, if this is the concentration profile, then after some time we might see a profile like this. At t3 we might get a profile like this. So, the concentration is continuously evolving. So, if we write this as T1, T2 and T3. So, at any particular time, let us say at T1 Ci is varying as a function of x, but if you consider at any particular x, Ci is also varying as a function of time, and that is the reason we are using the partial differentiation sign here. Now, you will see one of the limitations of Fick's law here, that it talks about concentration variation with respect to x, but it is not explicitly talking about concentration variation with time. So, if you want to predict the evolution of concentration, this equation alone cannot be used. Okay, that is one of the limitations of Fick's law, but anyway that does not mean that Fick's law is not applicable when C is varying as a function of time. In fact, at any given time you can apply Fick's law at any given plane along this concentration profile. Okay, now, there is one more thing, d tilde is a function of composition, and since composition varies with x and t, our diffusion coefficient in this equation is also varying with x and t. Okay, so, d tilde is not constant, that is not independent of composition, but it varies with composition, and since composition varies with x and t, d tilde varies with x and c. So, that has to be taken into account whenever we solve the equations for predicting evolution of concentration profiles. Okay, so, how do we overcome this? In order to take into account the variation of concentration with time also, so Ci is concentration of I is a function of x and t. In order to take into account the variation with time, we use what is called as principle of conservation of species. Right. So, if we consider a box into which there is a species I entering from some directions and there is also species I leaving from other directions. So, it is a simple equation, the rate of inflow minus rate of outflow will give me the rate of accumulation of component I inside this box. Now, when I say that, I am making one assumption. What is that?
Size is constant. Size of box is constant. No loss.
Yes. So, I am assuming that there is no production or loss of component I within this box. Okay. So, that is one assumption. So, one example where this can happen is if there is a radioactive decay of component I, right. So, you might lose some of the species of I, right. So, when this happens, you have to take into account the rate of production or loss also. Okay. So, let us assume that there is no production or loss of component I. Now, and let us consider the case of unidirectional diffusion, right. So, I am considering here the situation where I have a specimen along which there is some concentration gradient and the diffusion is occurring, right. So, this is my C I versus x and the diffusion is unidirectional, that is taking into this direction, let us call this plus x direction. So, now if I consider a small volume element which is bound by two vertical planes which are perpendicular to the diffusion direction, let us call this plane 1 and plane 2, and the cross sectional area of this specimen is, let us say it is A. Now, we know since the concentration gradient here is negative, right, this way the diffusion flux is from left to right. Let us say at plane 1 the flux is J I tilde 1 and this is at given time t I am talking about, right, and at plane 2 the flux is denoted as J I tilde at 2. Right. So, I can consider a plane in between, the width of this volume element is let us say delta x. Exactly at the center I consider one more plane and the flux there is denoted as J I tilde. So, if delta x is very small, I can express J I tilde at 1 and J I tilde 2 in terms of J I tilde and the gradient of flux with respect to x. So, I can write J I tilde at 1 is equal to J I tilde minus delta x by 2 times the gradient of flux J I tilde dou J I tilde by dou x at this given time t. And similarly, J I tilde at 2 I can write it as J I tilde plus delta x by 2 tilde by dou x, the gradient I am considering at the given time t here. So, now the flux at plane 1 is basically the incoming flux or the inflow into the volume element delta x, and the flux at plane 2 is the outflow, basically rate of outflow per unit time per unit area, right, that is the unit of flux. So, inflow minus outflow will give me the accumulation, right. So, if I write this equation, accumulation of I in small time interval delta t should be equal to inflow minus outflow, and what will the inflow Gi tilde at 1 times delta t times A, right, because the flux is per unit area per unit time, minus Gi tilde at 2 then delta t times A. So, I write accumulation of I in time delta t, let us denote it by delta n I divided by delta t times A should be equal to, if I substitute for Gi tilde at 1 and 2, this minus this. So, this will get cancelled, and so I get minus delta x times dou Gi tilde by dou x at time t, and A times delta x is nothing but the volume of the element that I am considering. So, delta Ni by volume is just nothing but the concentration in the units that we usually use, moles per centimeter cube or number of atoms per centimeter cube, whichever unit Ni is expressed depending on that. So, that becomes delta Ci by delta t, and this is I am considering at location x here, should be equal to minus, this should be dou Gi tilde by dou x at t. And if I consider very small time interval, that is as delta t tends to 0, I can replace this with again the partial derivative of Ci with respect to t. So, dou Ci by dou t at constant x is equal to minus dou Gi tilde by dou x at t, and this is the so called conservation equation or continuity equation. Now, this gives me Ci as a function of both t and x. So, this is the very fundamental equation, the continuity equation. Now, remember again, while deriving this, I assume that there is no production or loss of the species I. Typically, in the diffusion in solid that we consider, right, especially when the diffusion is defect mediated, like for example, vacancies, there may be production of excess vacancies or loss of vacancies to the sink, and that might affect this term Ci here, right, because it affects the site fraction of species I, right. So, in that case we need to also consider the rate of production or rate of loss of the particular sites or vacancies. Okay. For now we are assuming that there is no production or loss of species I. So, let us try to analyze the consequences of this equation. So, if I substitute fixed law equation in the continuity equation, I get dou Ci by dou x, dou Ci by dou t at x should be equal to, I write Gi tilde equal to minus d tilde dou Ci by dou x. So, negative sign will vanish. So, dou by dou x of d tilde dou Ci by dou x. Clear? Now, remember again, as I mentioned earlier, d tilde is a function of composition, and since composition varies with x, d tilde also varies with x. So, you cannot straight away take this out as a constant. Only when d tilde is constant or d tilde is independent of Ci, we can write dou Ci by dou t at x is equal to d tilde times second partial of Ci with respect to x. And this is commonly known as Fick's second law. It is not exactly appropriate to mention this as Fick's second law, but it is popularly known as, because the fundamental equation is Fick's law equation, J tilde equal to minus d tilde dou C by dou x. And then this is again the continuity equation is simply the principle of conservation. So, if you substitute Fick's law in the continuity equation, we get this equation. One more thing, this continuity equation is valid only in stationary frame of reference. Okay. So, I should more accurately write the continuity equation as dou Ci by dou t at x should be equal to minus dou Gi 0 by dou x at t, where Gi 0 is the interdiffusion flux in stationary, or which is also referred to as lab fixed frame. Okay. So, now based upon our previous discussion, when I wrote this, what is the assumption that I have made here? What is the frame of reference that we usually use when we write this equation? Volume fixed frame, right? And if I substitute the flux in volume fixed frame just like the flux in stationary frame of reference, what is the assumption that I am making? Right. So, volume fixed frame is coinciding with the lab fixed frame, that is when u v equal to 0, the velocity of volume fixed frame is 0, then only this can happen. Otherwise, we know Gi 0 equal to Gi tilde, this is in volume fixed frame, right. Gi tilde should be plus Ci times uv. So, when I substitute here, original equation becomes dou Ci by dou t at x should be equal to minus dou Gi tilde by dou x minus uv times dou Ci by dou x minus Ci times dou uv by dou x. So, if I want to write the diffusion equation in terms of fluxes in volume fixed frame, I also need to consider the velocity of the volume fixed frame, and only when that uv is 0 I get the original form of continuity equation, that as in the stationary frame of reference, because in that case the stationary frame and volume fixed frame overlap, coincide. And as I said, this happens when the partial molar volumes are assumed constant. In other words, when there is no net volume change occurring because of diffusion. If the partial molar volumes are functions of composition, then with diffusion there will be a change in volume, there will be net compression or expansion of the diffusion zone. And obviously, when there is an expansion or contraction, right. So, you can visualize along with the diffusive flow or the Fickian flux, there will also be the net mass flow because of the expansion or contraction. So, that you need to consider when you write the flux in lap fixed frame. Clear? So, when I write this equation, I am assuming that my lap fixed frame is coinciding with volume fixed frame, which in other words means the velocity of volume fixed frame uv is 0. Again, uv also varies with x, uv is not constant, it will change as a function of x and t. Clear? So, we will talk about this in more detail later, but at this point just understand that continuity equation applies only in stationary fixed frame. Clear? Okay. So, now with that assumption, let us try to solve this equation, we should call as diffusion equation. This is the basic diffusion equation which we should solve for different boundary values and initial conditions, right. You can see this is an equation, partial differential equation of second order in x and first order in t. So, how many conditions we need to solve these equations?
One initial condition, two boundary conditions.
Right. So, we need one initial condition, the condition in time, and two boundary conditions, condition in x, in order to solve this partial differential equation. Okay. So, let us try to solve these equations for different boundary and initial conditions in next few classes. Let us start with a very simple case, which is known as steady state diffusion. So, what is a steady state?
Concentration won't change with the time.
Right. So, the diffusion is occurring, but it is not causing any change in concentration at any given position. Okay. And the classic example is the experiment done by Fick. Remember what he did? He studied the diffusion of salt in water, and he developed a steady state for that. I explained this in previous class, right. And the way he conducted the experiment was a vertical tube through which salt was diffusing. So, the vertical tube contained solution of salt and water. At the bottom, this was basically the source of salt, this is the saturated solution of salt in water. So, the concentration was fixed, and this was almost an infinite source of salt. So, the concentration of this will not change because of diffusion. Similarly, this was pure water. So, this was a sink for salt. The water container was very large, right. So, the addition of salt from this tube by diffusion into this will not cause significant change in the concentration. So, this remained pure water. So, Ci or salt of concentration was 0 here, and it was again fixed at the saturated concentration at the bottom, and through this tube the salt diffused to the solution. So, from bottom to top, and a steady state was developed. Steady state means at any given, the x position is vertical here, right, the x axis. At any given plane, x plane, the concentration did not vary with time, although the concentration varies from bottom to top, but at any given x it was fixed. Now, what should be the flux condition for this to happen? Think of the volume element that we use to derive continuity equation. Accumulation is equal to inflow minus outflow, and there is no net accumulation or loss, which means inflow should be equal to outflow. So, the flux should be constant at any given position for steady state to develop. So, in this case Ci varies only as a function of x, not as a function of t. So, in this equation basically dou Ci by dou t equal to 0, which means from this diffusion equation we can write d tilde dci d2Ci by dx2 equal to 0. I am replacing the partial sign with ordinary derivative sign, because now C is only function of x, it is not a function of t because of the steady state. Now, you can easily solve this equation, right. So, d this is you will go, this is also 0. So, dci by dx is a constant, let us call this b. So, if we solve this further, we get Ci is equal to bx plus some constant a, and this is an we know equation of straight line. So, when d tilde is constant, the steady state profile that develops is a straight line. This is obvious from here itself, right. The second derivative is 0, which means the curvature is 0, which is basically the straight line. Another example of steady state I can give here is, consider a thin slab of steel, low carbon steel, let us call it basically, which is subjected to continuous carburizing on one side and decarburizing on the other side. You understand carburizing, decarburizing, right? Carburizing is addition of carbon onto the steel surface. Decarburizing means carbon is getting removed from the steel surface. Okay. So, now if we maintain the right conditions, so that the carbon potentials at the two end are kept constant, right, there will be a continuous carburizing occurring from one side, continuous decarburizing occurring from the other side, and in some time a steady state will be developed across the steel thickness, the slab thickness, right. So, some profile like this will be developed. Now, if I assume that diffusion coefficient is constant, then I know it should be a straight line. So, let us say zoom it to draw the concentration profile here. If I draw Ci versus x, so this is 0 and this is x equal to let us say L is the thickness of the slab, and on one side I know the concentration, let us call it left side concentration Cl, Cr is the right side concentration, and obviously this side is decarburizing, so Cr is less than Cl, and I know a steady state will develop if the d tilde is constant. And what should be that? We know at x equal to 0, Ci is equal to Cl. So, this will give me Cl is equal to A, and at x equal to L, Ci is equal to Cr. So, I get Cr equal to Bl plus Cl, or L is equal to Cr minus Cl over L. So, Cr minus Cl over L is basically the slope, sorry, B is equal to Cr minus Cl over L, which is the slope of this straight line. So, we can write Ci is equal to Cr minus Cl divided by L x plus Cl. So, this is the steady state equation when d tilde is constant. Now, what happens if d tilde is not constant, which should be typically the case? So, if d tilde is not constant, we cannot take simply d tilde out, right. So, we can write dou Ci by dou T at x is equal to dou tilde by dou x dou Ci by dou x plus dou 2 Ci by dou x2, and when the steady state develops, we can write basically dou we can replace with d, d2 Ci by dx2 is equal to minus 1 by d tilde d tilde by dx times dci by dx. So, now we need to know d tilde as a function of x, or in other words we need to know d tilde as a function of Ci. So, if d tilde varies with composition, we need to know how d tilde is varying with composition, otherwise we cannot solve this equation. Now, we can qualitatively see how the profile will look like. Will it be straight line? Obviously not. So, how this will look like? So, suppose d tilde increases with Ci, then what should happen? D tilde is increasing with Ci, that means here we know the concentration is decreasing from left to right, right. So, here d tilde is decreasing with x. So, this derivative d tilde by dx is negative, right, negative negative, this is positive. Now, dci by dx is here is negative, right, because concentration is decreasing. So, the curvature in this case will be negative. So, the qualitatively the concentration profile will look something like this, right. We will have a negative curvature. Oppositely, if d tilde increases with decreasing Ci or d tilde decreases with increasing Ci, then the profile will develop positive curvature. Right. So, qualitatively it will look like this. Clear? Any question? So, this was about the steady state. Now, when concentration does change with time, that is a non-steady state condition. So, we will solve this equation for different boundary conditions, initial conditions. We will like to assume d tilde as constant, then we can have analytical solution. So, okay. So, we will assume d tilde constant, so that we have an idea how the concentration profiles will behave for different boundary conditions. Okay. Any doubt? Question? Yeah.
On the curvature, won't the 1 by d tilde effect will be there? In that there will be a denominator
Yeah.
d tilde.
Right.
Won't the effect of
Yeah, but d tilde is positive, right? For binary, d tilde will always be positive. So, the magnitude obviously will be affected, but the sign will not. Anything else? All right. Thank you.